Hello, and a very warm welcome to this quiet space. I'm so glad you've found your way here tonight. Whether you're lying down with the lights turned low, curled up in your favourite chair, or perhaps just letting your thoughts begin to soften at the end of a long day, you are in the right place. This time is for you. Tonight, we're going to embark on a quiet journey together. A gentle exploration not of a distant star or a forgotten history, but of the very ground beneath our feet. We're going to listen to the slow, powerful story of our own planet, a story of immense forces and deep time, the story of why earthquakes happen. Now, I should offer a gentle little warning. I have tried my very best to make this journey as peaceful and soothing as possible, but there's a small chance that the quiet wonders we uncover might be just a little too interesting. If your mind finds itself gently engaged rather than immediately drifting off, well, perhaps you'll just drift off feeling a little wiser, a little more connected to the incredible world we call home. If you already feel a sense of calm beginning to settle over you, I would be so grateful if you considered giving this a gentle like, and maybe even subscribing for more quiet explorations like this one. It truly does help more sleepy minds find their way here, to this shared space of rest and gentle discovery. And if you feel so inclined, I always love to read in the comments where you're listening from. It's a beautiful thing to imagine this peacefulness spreading across the globe. As always, please remember that this audio is intended for relaxation and gentle educational purposes only, and is not a substitute for medical advice or treatment. So let's just settle in, take a soft, easy breath. There's nothing to do right now, nowhere else to be. Just this space, this sound, and the gentle unfolding of a story. What is an earthquake? It's a fair question, and one whose answer begins not with a sudden shake, but with a quiet, immense, and incredibly slow dance. The story of an earthquake is, first and foremost, the story of our planet's skin. Imagine the Earth, not as a solid static ball of rock, but as something more like a beautiful hand-painted ceramic sphere that has cracked ever so slightly into a handful of massive interlocking pieces. These aren't just small cracks, they're vast continent-sized plates. And they're not still. They're adrift, floating on a sea of something much hotter and softer deep within the Earth. This outer shell, this cracked ceramic sphere, is called the lithosphere. It's a word that sounds both strong and delicate, now doesn't it? It's made up of the Earth's crust, the part we live on, the familiar ground of continents and the mysterious depths of the ocean floor, and the very top rigid layer of the mantle just beneath it. Think of it like the shell of an egg, but an egg of planetary proportions. And what does this eggshell float upon? Something called the asthenosphere. It's a wonderfully gentle word for such a powerful part of our world. The asthenosphere isn't a liquid in the way we think of water. It's more like honey, or perhaps thick, warm caramel. It's solid rock, but it's so hot and under such immense pressure that it can flow very, very slowly, over millions and millions of years. It is this slow, syrupy movement in the asthenosphere that carries the rigid plates of the lithosphere along for the ride. It's a motion so slow that we can't perceive it with our senses. The North American plate, for example, is drifting away from the Eurasian plate at about the same speed your fingernails grow. It's a silent, patient and relentless movement, a few centimetres a year, a quiet planetary creep. But when you consider that this has been happening for hundreds of millions of years, those few centimetres add up to thousands of kilometres. They add up to the entire Atlantic Ocean. These immense wandering plates are what we call tectonic plates, named from the Greek word tecton, which means to build. And that's what they do. They are the master builders of our world. As they drift, they collide. They pull apart and they slide past one another, and in doing so they build everything we see. They build the towering, majestic peaks of the Himalayas, pushed up into the sky by the slow-motion collision of the Indian plate into the Eurasian plate. They build the deep, mysterious trenches of the ocean, like the Mariana Trench, where one plate is slowly bending and sinking beneath another, and they build the long, volcanic ridges that snake across the seafloor where plates are pulling apart and new Earth is being born from the fiery depths below. This constant, silent process of building and reshaping is the fundamental rhythm of our planet. It's a geological heartbeat, measured in epochs and eons. It's a dance of creation and destruction, happening on a scale that is almost impossible to truly comprehend. And it is at the edges of these plates, at the boundaries where all this pushing and pulling and grinding takes place, that the story of an earthquake truly begins. These boundaries are not smooth, clean lines. They are vast, jagged, and complex zones of friction and stress, where the immense weight and momentum of entire continents meet. Imagine the edges of two immense ancient stones rubbing against one another. There is no smoothness there, only the friction of millennia. These plate boundaries are the great fault lines of our world, the seams where the planet's creative and destructive energies are most focused. And they come in three main forms, each with its own distinct personality, its own way of dancing. First, there are the boundaries where the plates are gently, slowly pulling away from each other. These are called divergent boundaries. Think of them as the places where the Earth is slowly unzipping itself. The most beautiful examples of this are hidden from our view, deep on the ocean floor. Running down the centre of the Atlantic Ocean, for instance, is the Mid-Atlantic Ridge. It's a vast underwater mountain range. Here the North American and Eurasian plates are separating, and as they do, magma from the warm, soft asthenosphere below rises up to fill the gap. It's like a slow, silent wound that constantly heals itself with fiery new skin. When this molten rock meets the cold, dark water of the deep ocean, it solidifies, creating new crust, new seafloor, a quiet, continuous creation story written in volcanic rock. The earthquakes that happen here are usually shallow and relatively gentle, the small tremors and grumbles of a planet stretching its limbs. Is the sound of new ground being born. On land, this same process can create great rift valleys, like the East African Rift, where the continent of Africa is slowly being pulled in two. It is a process that will one day, many millions of years from now, create a new ocean. It is a geology of patience. Then there are the places where the plates are moving towards each other. These are the convergent boundaries, and this is where the most powerful forces are unleashed. Here, instead of a gentle parting, there is an inexorable collision. What happens next depends on the type of plates that are meeting. Often a dense, heavy oceanic plate will meet a lighter, more buoyant continental plate. The oceanic plate, being heavier, loses the slow-motion battle. It bends and begins to slide downwards, back into the Earth's mantle, a process called a subduction. Imagine sliding one piece of thick paper under another. The top piece might wrinkle and crumple a bit, and that's exactly what happens to the continental plate. Its edge is folded and uplifted, creating long mountain ranges along the coast like the Andes in South America. As the oceanic plate sinks, it carries water down with it. This water lowers the melting point of the hot mantle rock above, creating magma. This magma, being less dense than the rock around it, begins to rise. Some of it will cool and harden within the crust, but some will find its way to the surface, erupting to create a chain of majestic and often volatile volcanoes. This is why the rim of the Pacific Ocean, where so much subduction occurs, is known as the Ring of Fire. It is a place of immense geological activity, where the cycle of creation and destruction is on full display. But what happens when two continental plates, both too light and buoyant to be subducted, collide? This is where the planet's most dramatic mountain building occurs. The ongoing collision of the Indian plate with the Eurasian plate is the perfect example. It's like two impossibly vast and heavy rugs being pushed together. Neither one can slide under the other, so the only way to go is up. The rock crumples, folds and shatters, thrusting skyward to create the breathtaking, jagged peaks of the Himalayas and the vast, high expanse of the Tibetan Plateau. The Earth's crust here is twice its normal thickness, a testament to the colossal forces at play. Finally, we have the third type of boundary where plates aren't colliding or pulling apart, but are sliding past each other horizontally. These are transformed boundaries. Picture two enormous blocks of sandpaper sliding past one another. They don't glide smoothly, they catch, they snag. The edges are rough and they lock together. The immense engine of the mantle below continues to drive the plates, but at the boundary they are stuck. All the while the pressure builds. For years, for decades, for centuries, the rock strains and deforms, storing up energy like a coiled spring. The ground is being twisted out of shape, but the fault itself remains locked. It is a quiet, mounting tension, building silently beneath the peaceful landscape. California's famous San Andreas Fault is one of these boundaries, a place where the Pacific Plate is grinding its way northwestward past the North American Plate. It is a place of stored energy, a place of patience and immense gathering force. These three types of boundaries, divergent, convergent and transform, account for almost all of the earthquakes on our planet. They are the stages upon which this slow, powerful geological ballet is performed, each with its own steps, its own rhythm, and its own way of releasing the vast pent-up energy that accumulates deep within the Earth's crust. And so we arrive at the heart of the matter. We have these immense plates snagged on one another, locked in a silent contest of wills. The engine of the mantle pushes and pulls, but the fault holds fast. Year after year, the rock along this boundary is not breaking but bending. It is absorbing all of that relentless motion, deforming, stretching and compressing. It is storing energy, much like a wooden branch that you bend slowly in your hands. You can feel the tension building within it, the fibres of the wood straining. The branch is storing your energy as potential, or what geologists call elastic strain energy. For a time, nothing seems to happen on the surface. Decades, even centuries, can pass in this state of quiet, accumulating stress. But just like that branch, there is a limit to how much the rock can bend. Eventually, the accumulated stress becomes greater than the friction holding the two sides of the fault together. At a single point, somewhere deep within the crust, the rock breaks its grip. It slips. In that instant, all the stored energy from all those years of bending is released. The rock on either side of the fault doesn't just move to its new position, it snaps back, rebounding to its original unstrained shape. This is the beautiful and simple idea at the core of every earthquake, the elastic rebound theory. It's not the ground breaking that causes the quake, but the ground snapping back. The sudden, powerful release of that pent-up energy travels outwards from the point of the slip in all directions. It travels in the form of waves, ripples of energy through the solid body of the Earth. These are the seismic waves. The place where this slip begins, the true birthplace of the earthquake deep within the Earth's crust, is called the hypocenter, or sometimes the focus. It might be a few kilometers down or hundreds of kilometers down. It is the very heart of the rupture. And the point on the Earth's surface directly above it, the point we would mark on a map, is called the epicenter. While the strongest shaking is often felt near the epicenter, the earthquake itself, the actual release of energy, began its life far below in the quiet dark of the crust. These seismic waves, this unfurling of energy, are not all the same. They are a family of vibrations, each travelling in its own way and at its own speed. The first to radiate out from the hypocenter are the fastest and gentlest of the waves. They are called P waves, which stands for primary waves. They are primary because they are the first to arrive. A P wave is a compression wave. Imagine a stretched out slinky spring. If you give one end a sharp push, a wave of compression travels all the way down its length. The coils of the spring are pushed together and then pulled apart in the same direction that the wave is moving. This is exactly how a P wave travels through the rock of the Earth. It pushes and pulls the rock, causing it to vibrate back and forth in the direction of the wave's travel. They are the fastest of all the seismic waves, and they can travel through both solid rock and liquid layers, like the Earth's outer core. When a P wave arrives at the surface, it often feels like a sudden jolt or a subtle shudder, the quiet herald of the energy that is to follow. It's the planet's first deep announcement that something has shifted. Following behind the P waves are the S waves, which stands for secondary waves. They are slower, and they carry a different kind of motion. An S wave is a shear wave. Instead of pushing and pulling the rock, it shears it, moving it up and down or side to side, perpendicular to the direction the wave is travelling. Think of taking a long rope, holding one end and whipping it up and down. You can see the wave travel down the rope, but the rope itself is only moving vertically. This shearing motion is more complex, and it carries a great deal of energy. S-waves can only travel through solids, as liquids don't have the rigidity to support a shearing motion. When they can't pass through the liquid outer core, it leaves a shadow on the other side of the planet, which is one of the key ways scientists first learned that the Earth's outer core was molten. When S-waves arrive at the surface, their side-to-side or up and down shaking is often stronger and more pronounced than the initial jolt of the P wave. It is a slower, more rolling motion, the second chapter in the story that the earthquake is telling across the landscape. These two travellers, the P wave and the S wave, journey through the deep body of the Earth. But the story of the earthquake's energy doesn't end there. When this energy, born in the hypercenter, reaches the surface of our world, it transforms. It gives birth to a new set of waves. Waves that are trapped near the surface and travel along it, much like the ripples on the surface of a still pond after a stone has been tossed in. These are the surface waves, and because their energy is concentrated along the ground we live on, they are often the ones we feel most intensely. They arrive last, after the P and S waves, but they often bring the most complex and powerful motion. The first of these surface travellers is the love wave, a name that seems far too gentle for its motion. It is named not for the emotion, but for the British mathematician Augustus Edward Hoof Love, who discovered its existence mathematically in 1911. A love wave is a surface shear wave. It moves the ground from side to side in a horizontal motion, perpendicular to the direction it is travelling. The easiest way to picture it is to imagine a snake slithering across the ground. The snake moves forward, but its body whips back and forth from side to side. Love waves do the same to the Earth, creating a sharp, horizontal shaking. Because they don't waste energy moving the ground up and down, they can be particularly potent. They are often the fastest of the surface waves, and their side-to-side shearing is what can be most stressful to the foundations of structures, which are designed primarily to handle the vertical force of gravity. It is a purely horizontal dance, a whip-like motion across the surface of the landscape. Following the love waves, or sometimes intertwined with them, comes the final character in our story of seismic waves, the Rayleigh wave. Named for Lord Rayleigh, who predicted its existence back in 1885, this wave is perhaps the most fascinating of all. It is the one that most closely resembles waves on the surface of water. A Rayleigh wave rolls across the ground. It moves the Earth both up and down and back and forth in a circular rolling motion. If you could watch a single point on the ground as a Rayleigh wave passes, you would see it trace a small ellipse moving up, forward, down and back. It is this motion that can make the very ground itself appear to move in waves, like a heaving sea. It is a profound and often disorienting feeling, this experience of the solid earth behaving like a fluid. This complex rolling motion is the final, grandest expression of the energy released deep below. So, we have a sequence, a story that unfolds in waves across time and distance. First, the subtle, sharp jolt of the P wave, the primary announcement, then the stronger, shearing shake of the S wave, arriving from below, and finally the complex, lingering dance of the surface waves, the side-to-side slithering of the love waves and the deep, oceanic rolling of the Rayleigh waves. The entire event might only last for a few seconds, or perhaps for a few minutes in the greatest of quakes, but in that time the ground tells the complete story of the energy that has been released. It is a symphony of vibrations travelling out from that single point of rupture, the hypocenter, a symphony that carries with it all the power of continents in motion, of friction and release, of the slow, relentless dance of the tectonic plates. Each wave is a note in this planetary music, a message from the deep, dynamic heart of our world. And just as ripples on a pond grow fainter as they spread, so too do these seismic waves. Their energy dissipates as they travel across the globe, becoming ever more subtle, until eventually they are just faint whispers, detectable only by the most sensitive of instruments. These waves, these ripples of energy, travel across and through the entire planet. The grandest of them can circle the globe several times, their power slowly diminishing with distance until they become nothing more than a faint planetary whisper. But how do we listen for this whisper? How do we capture and read this intricate story written upon the very fabric of the rock beneath us? We listen with an instrument of profound sensitivity, an instrument designed to feel the faintest heartbeat of the earth, the seismograph. The idea behind a seismograph is beautifully simple, grounded in the fundamental laws of physics. Imagine you have a heavy weight, suspended from a frame by a spring or a string. Attached to this weight is a pen, and the tip of the pen is just touching a large piece of paper that is wound around a slowly rotating drum. The entire apparatus, the frame, the drum, the paper, is fixed to the ground. Now, when an earthquake's seismic waves arrive, the ground moves. The frame moves, the drum moves, the paper moves. But the heavy weight, because of its own inertia, wants to stay still. It resists the motion. And so as the paper shakes back and forth beneath the nearly still pen, the pen traces a line, a jagged, intricate record of the ground's motion. That recording, that elegant scribble, is called a seismogram. It is the Earth's handwriting. It is a direct, unfiltered message from the fault line, a graphical signature of a moment in the planet's life. Of course, modern seismographs are far more sophisticated than this simple mechanical model. They use sensitive electronics, magnets, and computers to detect and record motions far too small for a human to ever feel. But the principle of inertia, of a floating mass that remains still while the world moves around it, is still at the heart of their design. When we look at a seismogram, we can see the story of the earthquake unfold. We see the first small sharp wiggle in the otherwise quiet line. That's the P wave, arriving first as always. A few moments later, the scribbles become much larger and more agitated. That's the S wave with its more powerful shearing motion. And then, finally, the trace on the paper becomes a wild, high-amplitude crescendo of lines that can last for many seconds or minutes. These are the surface waves, the Love and Rayleigh waves, carrying their complex, rolling energy along the ground. But a seismogram does more than just record the shaking. It allows us to measure the earthquake's size. By analysing the height of the waves recorded on the seismogram, and by knowing the distance of the seismograph from the earthquake's epicenter, we can assign a number to the quake's power. This number is its magnitude. It is a measure of the total energy that was released back at the source, at the hypocenter, where the rock first slipped. Perhaps the most famous way of measuring this is the Richter scale. Though it has been largely succeeded in scientific circles, its name is familiar to us all. The Richter scale is logarithmic, which is a beautifully efficient way of handling incredibly vast ranges of numbers. What it means is that for each whole number you go up on the scale, the measured amplitude of the seismic waves, the amount of ground shaking increases by 10 times, but the energy released increases by even more. For each whole number step up on the scale, the earthquake releases about 32 times more energy. So a magnitude 6 earthquake shakes the ground 10 times more intensely than a magnitude 5, but it releases the energy of about 32 magnitude 5 quakes. A magnitude 7 releases the energy of roughly 1,000 magnitude 5s. The scale helps us comprehend the incomprehensible, to put a number to forces that are almost beyond our imagination. Today, scientists often prefer a more refined scale, one called the moment magnitude scale. It gives a more accurate measure of the very largest earthquakes. It is calculated by looking not just at the shaking, but at the physical reality of the fault slip itself, the total area of the fault that ruptured, and the average distance that the rock moved. It gives us a more direct measure of the total work done by the Earth during the quake, the total energy released into the crust. But the principle is the same, to listen to the whispers and the shouts of the Earth, and to translate them into a language that we can understand. So we have a number, a magnitude, that tells us how much energy an earthquake has released from its source. It is a single objective measure of the event's power, but this raises a gentle question. Does an earthquake of, say, a magnitude 6 feel the same everywhere it is felt? If you are standing on solid rock, 10 kilometers from the epicenter, is your experience the same as someone 100 kilometers away, living in a valley filled with soft soil? The answer, of course, is no. The lived experience of an earthquake, the shaking beneath our feet, is a much more local and personal story. And so, scientists use a different concept to talk about this. They talk about an earthquake's intensity. While magnitude measures the cause, the energy released at the hypocenter, intensity measures the effect. It is a description of the severity of the shaking and its impact at a specific location. An earthquake has only one magnitude, but it can have many different intensities, which are highest near the center and slowly fade with distance. To measure this, we don't use a complex instrument, but something far more human: observation. The most common scale for this is the Modified Mercalli Intensity Scale, or MI. It is a wonderfully descriptive 12-step scale, written in Roman numerals, that ranks the effects of an earthquake from what is barely perceptible to the most profound of changes. At the very bottom of the scale, at an intensity of I, the earthquake is not felt by people at all. It is a phantom quake, its passage noted only by the silent, sensitive needle of a seismograph. At intensities 2 and 3, perhaps a few people at rest, maybe on the upper floors of a building, might feel a slight vibration. It might be mistaken for the passing of a heavy truck. The motion is subtle, a quiet question from the ground. At an intensity of IV and V, the experience becomes undeniable. It is felt indoors by many and outdoors by some. At night it might awaken sleepers. Dishes and windows may rattle, and pictures on the wall might be knocked crooked. You can hear the building creak. It is a conversation now, the earth speaking in a clear and definite voice. As we move up the scale to 6 and 7, the conversation becomes more serious. It is felt by everyone. People might find it difficult to walk steadily. Furniture is shifted, and plaster might fall from walls in small amounts. The shaking is strong enough that it is noticed by people driving cars, who might feel as though they have a flat tire. The energy is palpable, a force to be respected. At the higher end of the scale, from 8 to 12, the intensity describes more and more profound effects, not just on our human world, but on the landscape itself. It describes the ground becoming soft and unstable, cracks appearing, and the very shape of the land being altered. At its highest levels, the scale speaks of the visible rolling of the ground and the nearly total transformation of the environment. It describes the full, awesome power of the planet's internal forces made manifest on the surface. But why does the intensity vary so much? The most obvious reason is distance. The farther you are from the epicenter, the more the seismic waves have spread out and lost their energy, and the gentler the shaking will be. Another key factor is the depth of the earthquake. A very deep earthquake, even a powerful one, has its energy dissipate significantly before it ever reaches the surface. A shallow earthquake of the very same magnitude, however, can result in much more intense shaking at the epicenter, because the energy is released so close to the ground we stand upon. And then there is one of the most interesting factors of all, the local geology. The type of ground beneath your feet can dramatically change your experience of an earthquake. Solid, hard bedrock tends to be very stable. It vibrates, but it doesn't amplify the shaking very much. But soft, loose, water-saturated soils and sediments, the kind you might find in a river valley or a coastal basin, behave very differently. They can act like a bowl of jelly. When the seismic waves enter this soft material, they slow down and their amplitude increases, amplifying the shaking tremendously. This is why two towns, even at the same distance from an epicenter, can have vastly different intensity values and experience very different levels of impact. The ground itself plays the final, crucial role in shaping the story of the earthquake's journey. We've seen how the ground beneath us can shape the story of an earthquake, how solid rock and soft soil can amplify or dampen its waves. This idea that location is everything can be broadened out from our own small patch of Earth to the scale of the entire globe. If the great seams of the planet, the boundaries where the tectonic plates meet, are where all this energy is exchanged, then where on our beautiful blue marble do we find these zones of constant conversation? When we look at a map of the world's earthquakes, a striking pattern emerges. They are not scattered randomly across the globe like fallen leaves. Instead, they form distinct, elegant lines. They trace the edges of the Great Plates. The vast majority of the planet's seismic energy is released in a few specific, very active regions. The most famous of these is a vast horseshoe-shaped path that encircles the Pacific Ocean. It is a name you have likely heard before, a name that evokes images of fire and immense power. The Ring of Fire. This immense zone stretches up the western coast of South and North America, across the arc of the Aleutian Islands in Alaska, down through Japan, the Philippines and Indonesia, and all the way to New Zealand. About 90% of all the world's earthquakes, and the vast majority of its largest and most powerful ones, occur along this ring. The reason for this incredible activity goes back to our quiet exploration of plate boundaries. The Ring of Fire is, in essence, a massive world-circling chain of subduction zones. Here, the dense floor of the Pacific Ocean is slowly, relentlessly sliding beneath the lighter continental plates that surround it. It is a place where the Earth's crust is constantly and quietly being recycled, returning to the warm, soft mantle from which it once came. This process of subduction, as we know, is a powerful one. The immense friction and the bending of the plates create the conditions for the planet's deepest and mightiest earthquakes. And as the sinking plate releases water into the mantle above it, it fuels the melting of rock that rises to create the iconic volcanoes that also define this ring. The snow-capped peak of Mount Fuji in Japan, the majestic Mount Rainier in Washington state, the fiery volcanoes of the Andes, they are all children of this same process. The Ring of Fire is where the planet is most vividly and actively alive, a place of constant creation and renewal. There is another, second major earthquake belt, though it is less a ring and more a long winding road of seismic activity. It is called the Alpide Belt, and it stretches from the Mediterranean region eastwards across the globe. It runs through Italy and Greece, through Turkey and Iran, before meeting the most spectacular result of continental collision on Earth, the Himalayas. The belt continues on into Southeast Asia, finally joining the Ring of Fire in Indonesia. This belt is not a story of subduction, but primarily one of continental collision. It marks the zone where the African, Arabian and Indian plates are all pushing northwards, grinding into the immense landmass of the Eurasian plate. The Alps, the Zagros Mountains of Iran, and most dramatically the towering Himalayas, are all wrinkles in the Earth's crust formed by this colossal slow-motion impact. The earthquakes here are the groans and stresses of continents buckling under incomprehensible pressure. And then there are the other boundaries, the quiet ones. The mid-ocean ridges, like the one running down the centre of the Atlantic, are also lined with earthquakes. But these are the divergent boundaries, the places where plates are pulling apart. The quakes here tend to be shallower and less powerful than in the collision zones, the gentle tremors of new Earth being born in the quiet dark of the deep ocean, far from human shores. Very rarely an earthquake will surprise us, occurring not at a plate boundary, but in the seemingly stable centre of a continent. These are called intraplate earthquakes. They're often a kind of geological echo, a memory of ancient tectonics. They happen along old, deep faults that were once active plate boundaries hundreds of millions of years ago. These ancient scars, buried deep in the crust, can remain as points of weakness. As the entire plate is slowly compressed and stressed by the action at its distant edges, these old wounds can sometimes be reactivated, releasing energy far from where we would expect to find it. They are a subtle reminder that the whole planet is a single interconnected system, and that the story of its past is never truly forgotten. We have traced the paths of these tremors across the globe, seeing how they concentrate along the great seams of our world. We've felt in our imagination the conversation of the ground, from a subtle whisper to a profound rolling motion. But is the shaking of the ground itself the only part of an earthquake story? Sometimes, the immense energy that is released, particularly under the ocean, sets in motion another, equally powerful event, a new character that enters the stage. This happens most often in the great subduction zones of the Ring of Fire. When a massive earthquake occurs, it's not just a horizontal slip. The seafloor itself can be suddenly and dramatically lifted or dropped. Imagine a section of the ocean floor, many kilometres long and wide, being thrust upwards by a metre or more in a matter of seconds. In doing so, it lifts the entire column of water resting above it, a truly immense volume of the ocean. That water, raised up by the seabed, is then pulled back down by gravity. As it falls, it creates a series of waves that radiate outwards, away from the epicentre. This is the birth of a tsunami. The word comes to us from Japanese, a combination of tsu, meaning harbour, and nami, meaning wave, a harbour wave. It is often miscalled a tidal wave, but it has nothing to do with the gentle, predictable rhythm of the tides. It is a direct consequence of the displaced water, a wave born from the earth itself. In the deep open ocean, a tsunami is a strange and stealthy traveller. It is not a towering wall of water. Instead, its energy is expressed as incredible speed and a vast wavelength. The wave itself might only be a metre high or even less, easily lost in the normal swell of the ocean. But its crests can be hundreds of kilometres apart, and it can travel across the deep ocean at the speed of a jetliner. It is a long, low, incredibly swift pulse of energy, passing entirely unnoticed beneath ships on the high seas. its true power hidden from view. The story changes dramatically when this swift pulse of energy reaches the shallow waters of a coastline. As the ocean floor begins to rise, the wave starts to feel the friction of the bottom. This friction slows it down. But all the energy it was carrying in its speed has to go somewhere. As the front of the wave slows, the back of the wave continues to rush forward at great speed, catching up. The energy begins to pile up. The wavelength shortens, and the height of the wave begins to grow and grow dramatically. The stealthy traveller reveals its true nature, rising from the sea as the water is drawn back from the shore and then returns in a powerful surge. An earthquake's energy can also have a strange and profound effect on the ground itself, especially in places where the soil is soft and wet. This phenomenon is called liquefaction. It is a word that perfectly describes what happens. For a few moments, the solid earth can behave like a liquid. Imagine a patch of ground made of loose, sandy soil, with water filling all the tiny spaces between the grains. Normally, the friction between all those grains of sand makes the ground solid and strong. We can walk on it, build on it. The sand grains rest on each other, supporting the weight above. But when the strong shearing S-waves of an earthquake pass through this water-saturated sand, the shaking can cause the loose grains to try and settle into a more compact arrangement. As they do, the pressure of the water in the spaces between them increases dramatically. If the shaking is strong and long enough, this water pressure can become so high that it pushes the sand grains apart. They are no longer touching, no longer supporting each other. They are just floating in the water. In that moment, the ground loses all its strength. It has, for all intents and purposes, become a liquid. A thick, sandy fluid. This is liquefaction. It is a temporary state, and once the shaking stops, the water pressure decreases, and the sand grains settle again, returning the ground to its solid state. But for those moments during the earthquake, the solid ground we take for granted reveals a surprising and fluid nature, another testament to the transformative power hidden just beneath our feet. We have journeyed deep into the earth and across the wide oceans, following the story of an earthquake's energy from its conception to its final expression. Knowing the profound power these events hold and the way they can reshape both land and water, it is only natural to ask a very human question. Can we see them coming? Can we know ahead of time when and where the ground will decide to speak? It is a question that scientists have pursued for generations, a quiet and noble quest for understanding. The truth is, at this moment in our journey of knowledge, predicting an earthquake in the way we predict the weather, stating a specific time, location and magnitude, is not something we can do. The earth holds its secrets close. The processes that lead to a rupture happen many kilometers beneath our feet, hidden from our direct view. The forces are immense, but the final trigger point, the moment a fault decides to slip, is governed by a chaotic and incredibly complex set of conditions. It is like trying to predict which specific crystal in a vast mountain of sugar will be the one to cause a tiny avalanche, and at what exact second. So instead of prediction, scientists focus on something far more achievable and, in many ways, more useful. They focus on forecasting. The difference is subtle but important. A prediction is a statement of certainty. A forecast is a statement of probability. It does not say, a large earthquake will strike this city next Tuesday at noon. Instead, it might say, based on our understanding of this fault, there is a 60% probability of a magnitude 7 or greater earthquake occurring in this region within the next 30 years. How do they create such a forecast? They become detectives of deep time. They look at the history written in the rocks, studying the records of past earthquakes in a region to understand its rhythm and character. They can dig trenches across faults to see layers of soil displaced by ancient quakes, allowing them to build a timeline stretching back thousands of years. They also identify what are known as seismic gaps. These are segments of very active faults that have been suspiciously quiet for a long time compared to the segments around them. This quietness is not always a sign of safety. Often it is a sign that this part of the fault is locked tightly, accumulating stress, like a portion of a spring that is being coiled more and more tightly. And today we have remarkable tools that help us see this strain building. Networks of incredibly precise GPS sensors are placed across the land. These sensors can measure the slow, silent creep and deformation of the Earth's crust, down to a matter of millimeters per year. We can now watch in almost real time as the land is warped by the inexorable movement of the plates below. We can see which areas are being squeezed, stretched, or twisted, giving us a clearer picture of where stress is building in the system. While we cannot predict the exact moment of release, we have developed an ingenious way to give a few moments of warning. This is the goal of earthquake early warning systems. These systems don't predict a quake, they simply outrun it. They work because of the different speeds of our familiar seismic waves. Imagine a network of sensitive seismometers located near a major fault. The instant an earthquake happens, the rupture begins at the hypocenter. The first waves to radiate outwards are the fast-moving but less destructive P waves. The seismometers in the network detect this first subtle jolt. Immediately they send out an alert. This alert travels not at the speed of the seismic waves but at the speed of light, through communication systems. For areas farther away from the epicenter, this electronic alert will always arrive before the slower, more powerful S waves and surface waves. The warning might only be a few seconds, or perhaps a minute if you are far enough away. It is not a long time, but it can be a precious one. It is enough time for automated systems to slow down trains, to stop elevators at the nearest floor, to close vulnerable valves in industrial plants. And it is enough time for people to receive an alert on their phones, a brief, intelligent whisper from the network, giving them a few moments to take cover before the strong shaking arrives. It is a beautiful example of using our understanding of the Earth's own physics to create a moment of safety. We have followed the story of the earthquake from the slow straining of the plates to the final fleeting moments of an early warning. We've seen how humanity, with patience and ingenuity, has learned to read the story of the shaking ground, to forecast its likelihood, and to listen for its first whispers. But there is another story here, another deeper gift that earthquakes have given us. We have spent our time following the waves that travel along the surface, the ones we can feel. But what of the waves that dive deep? What happens to the P waves and S waves that plunge down into the heart of our planet on a journey through the hidden interior? What stories do they bring back? For as long as we have gazed up at the stars, we've wondered about the world beneath our feet. What lies at the centre of the earth? Is it hollow? Is it fire? For centuries it was a realm of pure speculation, a place only accessible to fantasy and myth. We cannot drill to the centre of the planet. The heat and pressure are far too immense for any machine we could ever build. But we have found another way to see. We have learned to use the energy of earthquakes themselves as a kind of planetary scale ultrasound. The seismic waves, born in the rupture of a fault, do not just travel outwards, they travel downwards. They pass through the layers of the earth, and as they do they are bent, they are reflected, and they change speed, depending on the material they are moving through. And all over the world our global network of silent sensitive seismographs waits and listens for these returning echoes. By studying which waves arrive, and when they arrive we can piece together a picture of the world's unseen interior. The key to this incredible vision lies with our two old friends, the P waves and the S waves. You'll remember that P waves, the compression waves, can travel through both solid rock and liquid. But S waves, the shearing waves, cannot. Their side-to-side motion simply cannot be sustained in a fluid. This simple fact led to one of the most profound discoveries about our planet. In the early 20th century, scientists noticed a curious pattern. After a large earthquake, the seismographs on the far side of the planet would pick up the P waves that had travelled straight through the Earth's centre. But in a wide circle on the other side of the world, a shadow zone existed where the S waves never arrived at all. They had been stopped by something. There could only be one explanation. At the heart of our world, there must be a massive liquid layer, an ocean of molten metal that the S waves simply could not cross. This was how we discovered the Earth's liquid outer core. It was a shadow that illuminated the truth. But the mystery didn't end there. Scientists also noticed a smaller, more complex shadow zone for the P waves. By studying the way these P waves were bent, or refracted, as they passed through the very centre, they deduced that there must be something else suspended within that liquid ocean, a solid sphere. This is how we discovered the solid inner core, a ball of solid iron and nickel as hot as the surface of the sun, but kept solid by the immense pressure at the centre of the world. A planet within a planet. Every earthquake that happens sends new waves through this incredible inner structure. By timing the journey of thousands upon thousands of these waves, from countless earthquakes over many decades, scientists can do more than just map the layers. They can begin to create a three-dimensional image of the mantle itself. It's like a planetary CAT scan. They can detect vast, slow-moving plumes of hot rock rising from the core, and they can trace the ghostly remnants of ancient subducted plates, cold slabs of crust sinking deep into the mantle on their final journey. And so our perspective shifts. An earthquake is no longer just a release of stress on the surface. It is a lamp that we can use to see the unseen. It is the Earth's own way of revealing its deeper secrets to us. The very same energy that causes the ground to tremble becomes a tool of immense discovery, a form of illumination that brings back a portrait of the deep, dark and wonderfully complex world that lies just beneath our feet. Our journey together has shown us that our Earth is a living planet, not in a biological sense, but in a dynamic geological one. It breathes, it stretches, it shifts. Its surface is constantly being unmade and remade by the slow, powerful engine of its inner heat. We have come to know it as a world of immense energy and constant quiet motion. But is our home unique in this restlessness? Does this trembling happen elsewhere? If we could leave the gentle blue and white of our own world and place a seismometer on the silent grey dust of our moon, or on the cold red plains of Mars, what would we hear in the deep quiet of space? For a long time we didn't know, but then, during the age of the Apollo missions, astronauts left behind more than just footprints. They left instruments, including a network of seismometers that for years listened to the heartbeat of the moon. And they discovered that our silent satellite is not entirely still. It has moonquakes. Most of them are deep, originating far down in the lunar mantle. They are not caused by the shifting of plates, but by something much more familiar, the tidal pull of the Earth. Just as the moon's gravity pulls on our oceans to create the tides, the Earth's much greater gravity constantly pulls and squeezes the moon as it orbits. This relentless gravitational kneading creates stresses deep within, causing the rock to slip and shudder. They are the faint, regular groans of a celestial body in a constant gravitational dance with its partner. There are also shallow moonquakes, much rarer and more mysterious, that happen closer to the surface. And when these occur, something remarkable happens. The shaking can last for a very, very long time, 10 minutes or even more. This is because the moon is incredibly dry and cold. Its crust is a single solid piece, not a jumble of fractured, waterlogged plates like Earth's. And so, when it is struck by a tremor, it vibrates like a tuning fork or a bell. The seismic energy isn't dampened by water or softened by fractures. It just rings on and on in the silent vacuum. More recently, our curiosity has taken us farther. We sent a lander to Mars, a mission named Insight, whose sole purpose was to take the planet's pulse. It gently placed a sensitive seismometer on the Martian surface and began to listen. And in the thin, quiet atmosphere it heard them. Mars quakes. Mars does not have plate tectonics like Earth. Its geological engine has mostly run down, but it is not a dead world. It is a planet that is still slowly cooling from its formation billions of years ago, and as it cools, it contracts. It is very, very slowly shrinking. This shrinking puts stress on its rigid outer crust, creating cracks and faults. A Marsquake is the sound of this stress being released. It is the faint, low rumble of a planet settling in its long old age, like an old house creaking in the night. Listening to these faint tremors from other worlds does more than simply satisfy our curiosity. It helps us understand the story of all rocky planets. By comparing the quiet groans of the Moon and the slow settling of Mars with the vigorous, constant activity of Earth, we see just how special our own world is. Our planet's system of plate tectonics, this engine that drives the continents, builds mountains, and renews the crust, is a rare and precious thing. It is the source of the earthquakes we have been exploring, but it is also a vital part of what makes our world a vibrant, habitable, and ever-changing home. These tremors in the quiet of space remind us that we live on a world that is uniquely and beautifully alive. Our journey has taken us to the cold, quiet stillness of other worlds, listening for the faint heartbeats of the Moon and Mars. And in that immense silence we found a deeper appreciation for the unique, restless vitality of our own Earth. We have learned to listen to our planet with sensitive machines, translating its deep rumbles into lines on a page and numbers on a scale. But it is worth wondering, are we the only ones listening? Long before we built our first seismograph, have other creatures, more finely attuned to the subtle language of the natural world, been sensing these shifts all along? The idea that animals can sense an impending earthquake is an ancient one, a thread woven through human history and folklore. Stories from ancient Greece tell of rats, weasels, and snakes leaving the city of Helki in a mass exodus, days before a catastrophic earthquake and tsunami destroyed it. Accounts from around the world and across the centuries echo this same observation, of birds that fall silent or take flight in unison, of farm animals that refuse to enter their barns, of fish that leap from the water. These are stories, anecdotes passed down through generations, but their sheer persistence makes us pause and wonder. Could there be a quiet truth to them? Scientists, in their patient way, are exploring this very question, and while the mystery is far from solved, they have some gentle ideas about what might be happening. One possibility takes us back to the P waves. We know that these primary waves are the first to arrive, a subtle, high-frequency vibration that often goes unnoticed by us humans. But what if you were a creature with hearing far more sensitive than our own? What if you could feel that first faint shudder in the earth not as a curiosity, but as an instinctual signal of danger? It's possible that what we see as a prediction is simply a very, very early reaction to the first moment the earthquake has already begun, miles away and deep underground. Another idea lies not in vibration, but in chemistry. As the tectonic plates strain and the rock in the Earth's crust is squeezed to an incredible degree, it can cause subtle changes in the environment. Tiny cracks can open and close, altering the flow of groundwater. Dissolved gases that are normally trapped deep in the rock, like radon, can be released into the soil and water. Could it be that creatures living in the earth and water, amphibians, fish, or burrowing animals, are sensitive to these minute chemical changes in their homes? A change in the taste of the water or the scent of the air that is entirely imperceptible to us, but to them is a clear and urgent signal that something is wrong. And then there is the possibility of electricity. Some researchers believe that the immense stress on certain types of rock crystals before a rupture can generate very slight changes in the local electrical and magnetic fields. We know that many animals, especially birds and fish, use the Earth's magnetic field to navigate. Their internal compass is exquisitely sensitive. Is it possible that they can feel the subtle warping of this field as the ground strains, a distortion that our own senses could never detect? The challenge, of course, is proving it. Animal behaviour is complex and can change for many reasons. It is difficult to separate a true reaction to an unseen geological force from a reaction to a dozen other things. But the possibility remains a beautiful and humbling one. It suggests that the whole planet is a single, interconnected system, a web of subtle influences, that the deep, slow groan of a fault line preparing to slip might be felt not just as a number on a machine, but as a moment of stillness in the forest, a restlessness in the field, a whisper that passes through the Biosphere, understood by its oldest residents. It reminds us that we share this dynamic world with other listeners, creatures who may be hearing a conversation that we are only just beginning to understand. And so our quiet journey together comes to a gentle close. We have travelled from the slow, patient dance of the continents to the fleeting vibrations of a single seismic wave. We journeyed to the fiery heart of our own world, using the echoes of distant quakes as our guide, and then drifted through the profound silence of space to listen for the faint tremors of other worlds. We have seen that an earthquake is so much more than a moment of shaking. It is a story. It is the story of the Earth's life, a testament to the immense and beautiful forces that have shaped our planet and everything on it. Tonight, as you settle into your rest, you might think of the ground beneath you not as something static and unchanging, but as something alive with deep, slow rhythms. The same forces that push up the mountains and spread the seafloor are part of the story that holds you, a quiet planetary pulse beneath the stillness of the night. It is a reminder that we live upon a world of incredible power, but also one of profound and elegant order, a world that is constantly, quietly becoming. It has been a true pleasure to share this time with you, to wander down these paths of gentle discovery together. If you enjoyed our journey tonight and feel rested by it, I would be so grateful if you considered giving this a gentle like, or maybe even subscribing so we can meet here again for another quiet exploration. Your presence here helps this peaceful space grow. For now though, all that is left to do is rest. Let your thoughts soften. Let the deep, slow rhythm of your own breathing be your guide. The story is told and the world will wait. Sleep well, and until next time, keep wondering.